Okay, so obviously we've been talking about organic chemistry. We, believe it or not, I think pretty much kind of wrapped up the previous chapter there, 12. We did skip a couple of slides, but I believe we did them actually earlier in the lecture. But just to make sure, we were talking about definitely towards the end there, aldehydes and ketones. And remember that as we talked about earlier, alcohols is sort of where we get those guys. So when we do take a primary alcohol and we oxidize it, we do get our aldehyde. And we further oxidize it one more time. We will get to a carboxylic acid, which is what we're going to talk about here today. Remember, we're going to lecture a little bit here. We will stop early, obviously, and we'll take the quiz towards the last part of lecture. Secondary alcohol will oxidize to a ketone. Will not continue on to a carboxylic acid or anything like that. A tertiary alcohol, as we talked about, does not oxidize, again, because it is missing that hydrogen that's necessary to do so. The opposite reaction is the reduction reaction in each of these, going in this direction here. We sort of, for example, here, do this guy. Again, this being a primary alcohol, when we do oxidize it, we're going to take an H and an H off, giving us our H2, and again, giving us our aldehyde, which is this group right here. Further oxidizing this, we'll actually stick a oxygen there to get our carboxylic acid group, which looks like this, which is this group right here, and so forth. Secondary alcohol is really how we get our ketones. So, when we take a secondary alcohol, such as this guy, oxidizing again, removing the hydrogens there, giving us H2, and then making our ketone group there by double bonding our oxygen here. We talked about at the very end sort of two tests that you could do to verify perhaps if you did get down to a carboxylic acid. You can use the Tollens tests or the Benedict test. Tollens test turns silver, kind of like a mirror there. If it's positive, that means that this oxidation occurred, the aldehyde to the ketone. I'm sorry, the aldehyde to the carboxylic acid. Benedict test goes from blue, copper, and turns to kind of an orange and red, also signifying that this oxidation occurred. Obviously, you would get a negative test for both of those guys if you are starting with a ketone. Again, the ketone really will not continue on through the oxidation process here, as it's really missing the hydrogen to do so here on this carbon, so it will not do that. Any questions on that stuff we talked about last time? And if I'm not mistaken, that also is the last chapter, I believe, that will be on the upcoming exam, which I think is a week from today, if I am not mistaken. Any questions on any of that stuff there? Okay, then we're going to kind of continue on here. Actually, we're going to skip 13 for now, and we're going to go to chapter 14, which is basically the rest of the organic. And then we'll go back to 13, which is carbohydrates. I'm not sure why your book arranged it like that. Usually they keep all the organic stuff together. All right, so we're going to kind of jump ahead here a chapter to 14, but it really does go with what we've been talking about in terms of organic chemistry. Pretty much this chapter will then fill in all the rest that's left over. So we got our carboxylic acid, we have our esters, our amines, and our amides. These are nitrogen containing groups. Our carboxylic acid we just saw there, and our ester, kind of looks like a carboxylic acid a little bit, but does not have the OH at the end. Has an oxygen carbon sort of connection. All right, let us get into for the first stuff here, which is our carboxylic acid. So obviously, as we were just talking about a second ago, we can generate a carboxylic acid way back when there from our primary alcohol that goes through one oxidation to take it again to our aldehyde, and a second oxidation step that takes us to our carboxylic acid. Again, functional group wise, OH for our alcohol, our aldehyde is our carbon, oxygen, hydrogen there, and our carboxylic acid is this as the functional group. In sort of formulas and so forth, it is oftentimes kind of written like this, COOH. So if you kind of see that in a formula, it is the functional group for a carboxylic acid. For example, acetic acid is very commonly written like this. And basically, if you drew acetic acid, which obviously, as you can see now, is actually a carboxylic acid, it would look like this. And again, that COOH is the functional group there for our carboxylic acid. So it is very commonly seen in formulas written like that. It's got really two sort of groups on it. It's got the carbonyl group, which we talked about earlier, is a polar group, negative at the oxygen, more positive at the carbon. Also has the polar hydroxyl group, and that obviously is like in water and everything else, more negative on the oxygen, more positive there on our hydrogen in this particular case. How do we name these guys? Well, not surprisingly, it does still go back to how many carbons there are. It still goes back to the alkanes and stuff. So for example, if we took this guy right here, it has basically what I just drew, actually. It is acetic acid, as I just drew it, but its more IUPAC name is based on the number of carbons. So if we look at this guy, he has got 2 carbons. So 2 carbons is going to be based off of ethane. We're going to actually drop the E. And since this is a carboxylic acid, we're actually going to put OIC acid at the end of it. And this is what is known as ethanoic acid. By the way, it is also known as acetic acid, the major component there of vinegar, basically. Here we can see this is known as benzoic acid. This is our carboxylic acid group that's there, attached to a benzene ring. And again, that is where our name comes from, benzoic acid in this particular case. And this guy here, 1 carbon, if it draws 1 carbon, 2 carbons, 3 carbons, based off of propane, has again our carboxylic acid group right there. So we drop that out, and as you can see here, becomes propanoic acid. Now, this group, much like the aldehyde group, because it has this hydrogen here at the end, means that the carboxylic acid sort of functional group will always end up at the end of the molecule. So it's always got to end up at the end. So we do not necessarily give the location of where the carboxylic acid group is located, but we do give it the priority in terms of numbering. So whatever side this group is on, that should always be carbon number 1. So again, kind of like the aldehyde, because it always will end up at the end of the molecule. We don't have to give the location of it, of the functional group, but because it is going to be there and it is the functional group, it should still get the priority in terms of numbering. So we would number everybody else accordingly, with that carbon being carbon number 1. Any questions on that there? So here's really your simplest carboxylic acid you could have. That is one carbon based off of methane, dropping that E, putting the oic acid at the end of it, and then obviously our ethanoic acid. Um, if you had, for example, something like this. Actually, let me do this here. Get rid of one of those hydrogens. And we'll lay up like a chlorine. Now, when we would go to name something like this, again, we're going to go with the longest carbon chain that obviously contains the functional group, which is the carboxylic acid. So in this case, it's just straight across as 1, 2, 3, 4, 5 carbons. 5 carbons is based off of pentane. It is the carboxylic acid group here. So that's going to be pentanoic acid. Now, again, we do not need to give that carbon there a number in the name, but for numbering purposes, it does have to be carbon 1, which means next door is carbon 2, 3, and 4. Again, the importance of that is we can now see that our group should be at carbon number 4 here, and this would be 4-chloral pentanoic acid. So again, no need to name the carbon that group is at, but it definitely is always going to be carbon number 1. Any questions on that there? All right, so we take a look at a couple of examples here of naming. Let's see what we got going on here. Again, if we look at this, we could see our carboxylic acid group. I'll spit that out. We have really 2 ways you could get to 4 in this case. You just go straight across, which obviously would be this 1, 2, 3, and 4. You could also go straight across and up. And again, you could choose either way. In most cases, it will give you the same sort of name. But we'll take the straight across like they did here. So 4 carbons based off of butane becomes butanoic acid, as we have the carboxylic acid group. Spit that out. Again, this is going to be carbon 1 over here because that's where the functional group's located. And again, the importance of that, as we can see here in the name, that gives us the proper number that we should use for the groups attached there, which is 3-methyl butanoic acid. In this case, we got a benzene ring that actually has, and as you can see here, it is actually, kind of like hanging off the ring here. But that is our carboxylic acid group that's happening here. In terms of the benzene ring, where that guy is attached, that would be carbon number 1. Again, that's sort of where the functional group is. And again, here we would want to go clockwise or counterclockwise to give our groups here the smaller number. In this case, it looks like if we go clockwise, we do end up with the smaller number. Again, if we went counterclockwise or right on the outside, we would end up with much larger numbers, obviously 5 and 6 versus 2 and 3. And much like we've been talking about here in organic chemistry, it's always about the smallest number. So we would obviously want to go like they did there. And we would proceed to name it just like normal. We have 2, 3. Those are the positions of each of the chlorine groups. And because there are 2 of them in this molecule, that is where the dichloral comes from. And we end up with 2, 3 dichloral benzoic acid. Any questions on those guys there? Okay. Here's again some common names that are sometimes still used. And I would say for us, these 2 here, methanoic acid, sometimes called formic acid. So that is a very common sort of name that is still used. And definitely, I would almost say most people actually go with acetic acid here instead of ethanoic acid. Most people, again, do use acetic acid as sort of the common name. But ethanoic acid, again, IUPAC name. Here's a couple other ones. But, for us, definitely these two names here, formic acid, which is basically your methanoic acid, and ethanoic acid, which is basically your acetic acid, are definitely ones that you should kind of know those two names and that they're really the same thing and sort of used interchangeably. Now, here's some common carboxylic acids here. Formic acid, again, obviously you get a sting, it irritates the skin. Acetic acid is basically the main component in vinegar. So obviously, if you've had vinegar or seen vinegar, you obviously know it. All right, so why don't you take a go at this? Let's go with the IUPAC name for this guy. So take a moment and see what you come up with. Let's take a look at this one here. So clearly, hopefully, we can see the carboxylic acid group, which is obviously right here, just being line structure. Again, there is a carbon right there. And just to highlight it, obviously right here is our carboxylic acid part. We're looking for, again, the longest carbon chain that's got that attached. So might as well start right there. So that's 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. That to me seems like the longest. You could go down and then down again, but that is only 3 carbons, which obviously is a lot less. So what I count there? 5. 1, 2, 3, 4, 5. So 5 carbons, again, going to be based off of pentane. We're going to drop the E because of the carboxylic acid. This is going to be pentanoic acid. Remember, we do have a group attached off of here that's not part of the main chain, and it is this guy right here. And remember that when we do have just a line inline structure, nothing written at the end, that basically is a carbon with the appropriate number of hydrogens, which is really a methyl group. And because this is the functional group, we do need to start numbering right here at this carbon. So that would be carbon 1, which means our methyl group should be at carbon number 2. So that's going to give us a 2-methyl pentanoic acid. Any questions on that name there? Okay, so why don't you try these two? Just go name the guy on the left and name the guy on the right. Okay, let's take a look here. So we'll start right here. Again, if we kind of put a box around it, that's our carboxylic acid group. We want our longest carbon chain, and it really does look like it is 3 no matter which way you go. You could go straight across for 3. You could go straight and then up for 3. So we'll take this straight across route here as our longest continuous carbon chain. So that is 3 carbons, which means it's based off of propane. Because it's a carboxylic acid, we're going to then become propanoic acid. This, of course, being carbon number 1, where our functional group is at. That would make that carbon 2 and that carbon 3. And that tells us that our methyl group is hanging out at carbon number 2, giving us, putting it all together, 2-methyl propanoic acid. Any questions on that one there? Here on the guy on the B, we again see our carboxylic acid. We also see that it is attached to a benzene ring, right? So that's basically a benzene ring with a carboxylic acid. Kind of think of it as all one piece there. And that one piece is really going to give us the base of our name, which then would be benzoic acid. Also a reminder that, when we see a ring that has no double bonds, that is cyclohexane. But here, when we see a ring that has 3 double bonds, That is benzene. Our reminder as well, sometimes it is drawn like that with a circle in the middle. So because this is really where the carbons attach to the functional group, has to be carbon number 1. If we go clockwise, that puts our group at carbon number 3. Obviously, if we go counterclockwise, we will end up with a 5, which is too large of a number. So we again would want to go with the 3, putting that into our name, 3-bromyl. I left a big space there, benzoic acid. Again, all kind of together. Any question on those two names? Okay, so like normal, you in addition to obviously need to name it, you do need to be able to draw some of these. So here's one to draw. Why don't you do the condensed and the line structure for this guy? And why don't you add to it 4-bromol 2-methyl pentanoic acid. And why don't you do 3 diethyl we'll do 3,3-diethyl hexanoic acid. All right, take a couple minutes and draw those guys. Got the name, you want to draw it. We just want to work, as always, backwards. So first off, when I see oic acid, that should tell me it's a carboxylic acid, and it should obviously have this group attached. Hexanoic acid is basically based off of hexane, which means, again, if we're going to do the condensed guy as well, you can really just start with your 6 carbons there. Because it's a carboxylic acid, and really because you are drawing it, you do have the option. We know it's going to end up at an end. You can put it on the left-hand side, or you can put it on the right-hand side. I personally am going to go and put it over here on the right-hand side. And there's our carboxylic acid group that has 6 carbons attached. Now, because I chose to put that group over there on the right-hand side, that does make that carbon number 1 for sure. And that's important because I see at carbon number 4, I need a chlorine. So that's 1, 2, 3. Number 4 should be right there. At this point, there's really nothing left but to put our traditional hydrogens in. This guy needs 2 to get him to 4 bonds, needs 2, actually just needs 1, needs 2, and needs 3 in this case. Any questions on that there? We're going to do line structure. We're looking at 6 there. So 1, 2, 3, 4, 5, and 6, I believe. I count that right. 1, 2, 3, 4, 5, and 6. Obviously, here at the end, we would have this type of deal happening. This again being our carboxylic acid, that would be carbon 1 there, 2, 3, and 4 in my picture. And I would lay up a chlorine in this case. Any questions on that there? Working the next one the same way. We're going to go with, again, oic acid, which tells us it's a carboxylic acid. We're going to go with pentane, which tells us it is 5 carbons in this particular case. Again, I'm just going to personally put the carboxylic acid group over here at the end. Once again, making that guy for me on the right, number 1. That takes care of that and that. That means that carbon number 2, there's a methyl group. So right here should be a methyl. And at carbon number 4, there's a bromine. So carbon number 4 would be here. Everybody else going to be hydrogen. So we need 1 there, couple there, 1 there, and 3 here. And that would obviously be our condensed formula for whatever I just crossed out there, 4-bromo 2-methyl pentanoic acid. If we're going to line structure this guy again, kind of the same idea. 1, 2, 3, 4, and 5. 1, 2, 3, 4, 5. Again, we would want to put our carboxylic acid group at the end. That would be carbon 1. Carbon 2 would have a methyl group. Just a single line is supposed to be. 2, 3, and 4 would have a bromine group. Any question on either of those two? Coming here again, hexanoic acid. So just like above, we will have a 6-carbon run here. 1, 2, 3, 4, 5, and 6. 6. I guess I should write carbon, not 6. Try that again. But at least I'm counting. I guess that's good. That is 6 there. Now why not? We'll mix it up. I'll put the carboxylic acid group over here on the left just to make it different. Now, since I put it on the left, that means that that is going to be carbon number 1 in my example here, which means carbon 3 is right here, and it's diethyl. So that is a 2-carbon group on both of these. And everything else here going to be hydrogens. And if I can find where I'm writing, there it is. H3, H2, H2. This guy doesn't need any. And this guy needs 2. And this guy right here doesn't need any. Again, that's not a line. That's just carbon number 1 written there. So it doesn't need anything. Line structure here, kind of similar to the one up here. 1, 2, 3, 4, 5, 6. Again, with our carboxylic acid group happening here. And we are looking for 3, 3 diethyl. So 1, 2, 3. And again, I'm scribbling some bad lines there. Let's try that again here. Write some of that here. All right, number 3, which would be that is 1, 2, 3. Again, we would have something like this: 1, 2 carbons, and something down like this, which would be 1 and 2 carbons. Any questions on drawing or naming carboxylic acids?
Yeah, Professor, I have a question.
Yeah.
When we're submitting the answer, which one are we submitting? The one with the lines, or the where it goes like CH3, CH2? Which one are we? What's the correct answer that we're supposed to be submitting?
It really does depend on sort of the question and what it asks. So for example, this particular question before I changed it asked for the line structure or the line angle structure, and that would be just the line guy. Now, I also asked you to draw the condensed structure, and this is condensed structure. So it does depend on sort of the instructions. So if it does say condensed, it should look like these guys over here specifically. So, you know, if it says condensed, you need to draw something that looks like the guy up there on top. If you drew the line structure, technically would be wrong because that's line structure. So the question will clearly say, you know, either there's basically kind of 3 structures you could draw. One would be the condensed, like the guy up there on top, where we don't draw out the hydrogens, we use the carbons. One would be line, where we really don't draw out any kind of carbons or anything like that. We just use lines. And one was referred to as the expanded structural formula, where you just basically draw out everything like this.
Which is the condensed and the line.
Yeah, so this is basically what I'm drawing right here is considered expanded structural formula, where we draw out all the bonds. The guy on the top and the other ones that we did that look like this, where we don't draw out the bonds to hydrogen, are what are referred to as condensed format.